Fantastic. So yeah, so Anil, let me give a quick intro. I'm VP of Business Development for ZeroPoint. And so the first question is, yeah, who is ZeroPoint? ZeroPoint is a IP licensing company based out of Sweden, and we do one thing, and we do it really well, which is memory compression across the hierarchy. So this is a portable solution. It's complementary solution to DRAM. It's complementary to CXL, and it's complementary to, in general, what the ecosystem out here is aiming to do, which is boost the capacity and performance of AI systems and cloud computing in general. So our IP, and I'll show you some more details, boost the memory capacity by 2 to 4x without, of course, inserting additional memory banks. And then this technology is 1,000 times faster than software solutions, which are prevalent today. And as a result of this, you can lower your total cost of ownership by 20 to 25%. And essentially, this technology is also used or can be used in consumer applications. And by the way, we have actually provided this to smart device customers where the impact is different, which is better battery life and user experience, whereas we're talking about data centers out here. So it's really the focus is on total cost of ownership reduction. So just a quick overview of the IP products that are available out here from the ZeroPoint portfolio. So if you look at the memory hierarchy picture that's drawn out here on the left, so there are several IP products. We offer products for SRAM, on-chip cache compression, and then main memory expansion and compression. So those are the two products out here, the SuperRAM and Ziptillion. But the one we'll focus on today is this product called DenseMem, which is geared towards CXL expansion. So even before I jump into the solution, let's first talk about what really is the challenge. So we've heard from now several presenters over this day about the challenges facing the explosion in AI, the cost of DRAM. We saw Memberge put up some of the parameters for the effective cost of these systems, and we know memory is the largest spend in the data center. Now, out of that, and in addition to memory, the hyperscalers today are spending significant amount of resources employing software-based compression. And both Meta and Google have published papers detailing out all the gory details of all the different compression, decompression algorithms that run at scale in the data center. So that's one challenge. Then this can add up to a pretty penny if you look at the infrastructure outlay at hyperscale. On the second side, recently, and when I say recent, this is at the end of October, the OCP consortium actually came out with the hyperscale CXL tiered memory expander specification. And so this we believe is a critical thing for the hyperscale adoption of CXL, and that's why it's made its way into a spec. So of course, with challenge comes opportunity, and the opportunity out here is, and as described in the hyperscale, the OCP CXL tiered memory expander spec, is the opportunity to add a compressed CXL memory tier into our devices. So the opportunity really is to deploy a new tier. We already have two tiers with DRAM and then, of course, CXL. Now we can have an additional layer, which is DRAM, ordinary CXL connected DRAM, and then a compressed DRAM memory on the same CXL device. And if you go through the spec, there's really three tenets which are the focus of this spec. One is reduction in the TCO. The second is energy efficiency and sustainability. But then there's also a third angle, which is to preserve software investments. So of course, hyperscalers and enterprise customers have invested significantly deploying solution, software solution. So of course, we don't want to have to throw away all those solutions and start from scratch. So those are the basic tenets, and there's more detail provided in the OCP spec. But the key takeaway is this spec has the potential to remove the barriers that and all kinds of TCO barriers that maybe we've heard several people talk about in the past in driving this CXL adoption broadly at hyperscale and enterprise customers. So let's, doing a double click into the requirements. If you read this specification for the tiered memory expander specification, so like I said, the tenets are pretty clear, and it needs to support legacy compression algorithm. So there's an explicit section on compression, and that calls out the algorithms that need to be supported, and then the latency and bandwidth specification. So again, we heard from XCon and we heard from several other presenters talking about the heavy focus on latency. So it's no different for compression capabilities. If you're going to do a compressed CXL tier, the latencies need to be extremely stringent as specified by the hyperscalers. And the bandwidth efficiency needs to also be significantly high. Now, in the spec, calls out for LZ4 as a minimum, but it leaves the door open for innovation algorithms. So if you look at some of the standard algorithms that exist today, like LZ4 and Z standard, so these are all geared towards the microsecond domain. And of course, as we all know, for CXL, we need to be in the nanosecond domains. And if we can do even better, if we can go down to single-digit nanoseconds, that's even better to help support and add new features, add new innovation to drive adoption of CXL technology. So the proposed solution, if you go through the spec again, is if you think of a CXL Type 3 device, like a memory expander, so in addition to your normal uncompressed tier, which is what you would have as on a standard CXL device, the proposal is then to add a compressed tier. And the way to do this is to add a hardware accelerated compression, decompression capability inside the the memory controller itself. So if you look at if you zoom into this CXL controller device, what it would look like is essentially a piece of IP block which could compress and decompress data as it's coming in at line speed, and then plugging in nicely in between the CXL interface and then on the other side before the data hits the DDR interface. So that's really the crux of the solution. And so then the question is, where does ZeroPoint come into this picture? So the ZeroPoint solution, we actually have an IP block. It's called DenseMem. This is OCP spec compliant. It's hardware accelerated IP block, which actually does three things. It does compression, decompression, of course, but then it also manages compaction and transparent memory management. So that makes it kind of smooth to integrate it into the software stack, and also to integrate it into a diversity of memory controller SoC devices. And while meeting the spec, ZeroPoint, the DenseMem IP delivers 2 to 4x compression, which has been tested on a variety of data center workloads. And in addition to the minimum algorithm support, which is called out in the spec, which is LZ4, we also have a proprietary algorithm which operates at cache line granularity. So that's one thing to take away from here is the algorithms, the compression, decompression algorithms that exist today in the market or in open source. They all operate at a page block granularity, which, of course, at the speed of CXL, when you're doing load stores, and there were several discussions earlier comparing load store access versus RDMA. So in this case, again, it's no different. If you want the highest performance, lowest latency, you have to be able to operate at the cache line granularity. So you're not waiting for entire blocks to be pulled in or to be delivered before you can do compression or decompression, which is why a lot of these algorithms are great for storage use cases, but the latency is too high in the microseconds. We need to do this in nanoseconds, and that's what the ZeroPoint solution achieves.
Now,
The IP is, yes,
there's
please.
a question for you. Is ZeroPoint involved in enabling the software ecosystem to adopt CXL hardware-based compression? If so, please explain what is being done.
Absolutely. Then I think that's a great question. So one of the things we are working on is, of course, making sure that this solution integrates nicely into the existing Linux framework ecosystem, the CXL drivers that are being developed. So yes, we do have a plan to develop like a test driver, if you will, which can act as a baseline for other customers to adopt it, or maybe in the future we might even upstream this. But this is something to work with the end users, because a lot of the hyperscalers may have custom solutions, but different enterprise customers have their own requirements. And actually, you'll see that's one of the call to actions I have at the end, is to call for collaboration to accelerate the development of the software driver stack, so that such capabilities and such innovation can be supported for our end customers jointly. So I'll come back to that. But yeah, this is an OCP compliant IP block solution. And then I was talking about the total cost of ownership. So when you think about the dollars per gigabyte, and you look at the rack scale TCO models that we can create, and of course certainly we saw that from Member at some of the total solution. So this is where there's an opportunity to reduce the total cost of energy pretty significantly, about 20 to 25%, and this is what end customers are really looking for at the end of the day. You want to run these LLM models that Lightelligence showed earlier, which are fantastic. But then you have to be able to do it within a compelling total cost of ownership. And of course, removing some of the excess cycles, for example, CPU cycles, that could be used somewhere else. For example, a hyperscaler could rent out those CPU cycles, which are being used for compression, decompression today, and then monetize those kinds of, get higher utility. So we did have a demo actually at Supercompute, and this was an FPGA based demo. I won't play it in the interest of time, but there is a YouTube link. Oops, it seemed to switch back to slide one. But let me put it out here. Yeah, so this is an FPGA based demo, which actually shows the compression decompression capability working within the framework of CXL, which was implemented in QEMU. So you can see the demo actually in on the YouTube link, which and maybe I'll just stick to this. I won't run it live right now, but essentially what we were demonstrating was inline transparent compression and decompression, and this number out here, this is showing the memory expansion factor, and we're running a variety of different data center workloads, and then also splitting up and managing the memory in two different tiers, uncompressed and a compressed tier, and then essentially also showing kind of a high hit ratio on the dense mem IP page cache. Once we decompress cache lines, that can then be used, and you don't need to necessarily go fetch them from DRAM. And of course, the performance numbers here are low, but this is an FPGA implementation with QEMU. But the same IP is targeted for production, and it will run at full CXL line speed. But at least this was the same RTL, which was used to demonstrate it in operating in FPGA in the CXL stack.
We have another question, Nilesh,
Yes,
if you mind. It's
yeah.
Where is the power savings coming from? Is it by offloading the compression from host CPU to CXL device-based compression?
Yes, that is one source of power savings, but the other source of power savings is essentially having this kind of compressed data essentially stored, right? So you can store more with less. That's the second angle. And then the third angle is when we already have this decompressed data available in our cache, that's providing additional benefits by not having to go out to DRAM. So yeah, there's like the TCO model that we computed kind of takes a holistic viewpoint into how we can save power and then also provide the performance that's required from the spec. Okay, let me move on. So yeah, we, like I was saying, we have characterized, and by the way, in the slides there's a link. It's a YouTube video link which shows the demo actually running, and it shows the diagram of how we emulated the CXL in QEMU with this implementation in FPGA. And so yeah, so across a variety of workloads, what you're looking at out here, there are three colors. The first one is let's just start with the yellow bar. That's LZ4. So that's a 4 KB block. That's our implementation of LZ4. So that's our estimate where LZ4 will land in terms of the compression ratio for various data center benchmarks. The second one, if you look at the purple bar, that's actually our cache line granularity algorithm. So that's the one that's operating at extremely low latencies. And like I said, we will have both these algorithms as part of the IP block. So that can actually deliver fairly competitive compression ratios. There is some trade-off, as you can see on some of the workloads where the compression ratio is lower, but it's doing this at extremely low latency, which is critical for many applications. And this will be a kind of an option that the customers will have to pick and choose which algorithm to apply for different use cases. So wrapping up then, and with a summary and a call to action. So the key takeaway is this DenseMem IP. This is OCP compliant. It's portable across the latest process nodes. It's also portable because it's an SoC chai interface, so it should plug into most SoC plumbing. And then this will be production ready mid 24, and we verified the performance with several data center workloads. So really the call to action to our community out here is one for controller manufacturers is to collaboratively address the hyperscale OCP requirements so we can accelerate the uptake and deployment of CXL technology. And then the earlier question that was asked saying, hey, and how do we integrate, how will all this work in the software stack? So of course, we have already been developing the software solution and the driver integration, etc., on the CXL side. But this is where we are also looking for community collaborators and having deep insight into the end user workloads and environments. For example, Member showed some of the end use applications, and there was sorry, go ahead. Was that a question? Yeah, so yeah, that's where we would like to collaborate with this ecosystem to accelerate this uptake of these innovations, which is what the end customers are asking for it. So let's deliver these capabilities jointly. So with that, I'll wrap up and hand it back to you, Frank.